Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas?
Why do some things glow in the dark?
Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Dave Ansell. Let's go straight into the questions. Andrew in Cambridge always likes to get a question in early. He says, does liquid nitrogen freeze? And if so, does the frozen nitrogen still conduct electricity like nitrogen does?
Yes, liquid nitrogen does freeze. You've got to get it at a lower temperature than liquid nitrogen. Nitrogen, room temperature, is a gas. It makes up about 80% of the atmosphere. If you cool it down to minus 196, then it turns into a liquid. If you then cool it down even further, if my memory serves me correctly, down to sort of minus 205-6 degrees centigrade or so, it will then condense, crystallise to form a solid. If you take liquid nitrogen and you pump gas away from it, it will cool it down, and eventually you can form little snowballs which float around in the liquid nitrogen. It's not something I've ever seen, but I really want to try it one day.
I'm sure you will do.
One of these days. I've got the kit. I've just got to get hold of the nitrogen and remember to do it. And so it will freeze. It's a sort of transparent solid, crystalline solid. Nitrogen gas doesn't conduct electricity very well. You can make it conduct electricity if you put a very, very large voltage through it. And then you get what's a spark, basically. You rip the electrons off the atoms, then you've got lots of free electrons which are floating about, which will conduct electricity quite well. But that takes lots of energy. That energy is released in the form of light and sound and things. So that's what you hear when you have a spark. Liquid nitrogen is a fairly good insulator. It's sort of as good as oil or something like that. I don't have any information on solid nitrogen, but I would guess it's similar. Not a fairly good insulator.
Ian asked me earlier, Ian Puckey, who's on BBC Essex, he said, I wonder if we could ask the Naked Scientist, why can you taste eye drops after putting them in?
I think what's going on here is you have a little duct which goes from your eyes, sort of little sinus, which a tear duct, which tears drain through into the back of your nose and then down the back of your throat. So any eye drops you put in behave just like tears and will just drain through these tear ducts into your nose, into your throat. And if the eye drops you put in have a strong taste, the stuff in them will end up in your mouth, or end up in the back of your throat and through your nose and your mouth. So if they taste of something, you'll taste them.
Now, Dave, Ralph in Stanford says, to have a digital clock, it changes when the clock changes, but it took until early Sunday morning to switch over. My watch does a similar thing, and it was early Monday when it switched over. Why does it take so long for auto-switching clocks to in fact switch to the right time?
I think you'll find there's various different types of auto-switching clock. There are the ones a bit like the clock in your computer, or probably quite most watches, which just know what the date is in their little computer inside, and they know when the clocks should change. There's probably some rule, I don't know the exacts about it, there's some rule which you can predict when the clock's going to change for the next 50 years. And so they've got those programmed into them. If it knows which year it is, then it will change the time
like a computer
on the right date, like a computer one does. Yeah. My guess is to the one which only changed on Monday is that he might have it set to the wrong year. So it's changing it. It thinks it's the right date on the wrong year. So thinks it should. So otherwise, I can't see why it would change on a Monday. You also get clocks. Those should change at the right time of night as well, because I know exactly what it is. You also get the radio controlled clocks, which might be his wall clock, which basically you don't have to set them. Occasionally, there's a signal which comes. There's a big atomic clock somewhere, possibly in Rugby, which transmits a time signal on a radio wave, and so it's every 15 minutes, every hour. It sends out a signal and says the time, a bit like a speaking clock, but in the digital signal, which the clock can understand, then picks up that signal and sets it to the right time. If you haven't got a very good reception to that signal, it might take a while for it to actually decide that it's actually picked up the signal. And so it might take a while, a few goes, until the atmospheric conditions are exactly right for it to pick up the right signal. So that could take a few hours, and then it will only change when it says, actually it shouldn't be 2 o'clock, it should actually be 1 o'clock. Or it should be 5 o'clock, it should be 4 o'clock, whatever. Otherwise, I can't think why it would be changing at odd times of the morning.
Confuse o'clock. Now, next one coming up your way is from Kev in Great Yarmouth. He said, how long does a domestic cable need to be for nothing to happen at the bulb when you turn the switch on?
Nothing to happen is a slightly difficult concept because you'll always get a current flowing however long that cable is. So basically I can give you some idea of how quickly it would die away.
Right.
And that actually depends on how big the bulb is. If you've got a 100-watt light bulb on the end of it, on the end of a long cable, and you've got a fairly standard domestic extension lead, to mean the resistance of the extension lead was about the same as the resistance of the light bulb. So that would double the resistance and mean you get a quarter of the power out of the light bulb. That would mean you need about 7 kilometres of cable. So that's pretty long. The light bulb would be on, but really quite dim at this point. You'd only be getting 20 watts of light. It would only be producing sort of 25 watts at this point. And because it's when a light bulb isn't on very brightly, it's going to be quite dim because it's going to be colder than it would be. So it'd be very yellow light. But if you had a 1 kilowatt single bar electric fire, because that's got much lower resistance, you need a much shorter cable to have the same effect. So you'd only need 300 metres of cable to halve the power that was using. And if you had a more powerful thing, even less. And if you want to use electrical devices which are more sensitive to reductions in voltage, and that's a really big drop, then you'll notice it over sort of 30 or 40 metres. I've noticed it with big fans on 30 or 40 metres of extension lead before.
Let's have a look here. What else have we got? Dave in Norwich says, I know we're in spring, but why is it that you can have torrential rain that lasts for hours, yet when it snows for hours, it never seems to be as heavy as when it rains? Good question.
Very good question. I think what this is to do with the amount of water that air can hold. The closer the temperature of air is to the boiling point of water, the more moisture it can hold. The closer you get to the boiling point of water, the amount of water it can hold goes up sort of exponentially. You can get a huge amount. If you've got air at sort of 95 degrees centigrade, it can hold a ridiculous amount of water. So the colder the air is, the less water it can hold. And so the less water there is there to drop out. So the less precipitation there can be. So if it's raining, a really heavy rain, that's normally from warm air at sort of maybe 20, 30 degrees centigrade with lots of moisture in it, meeting very cold air at 0 degrees centigrade, condenses the water out, and it all falls as rain very quickly. With snow, on the other hand, if you can't start off with air too warm, because otherwise it's not going to end up as snow. It's not going to cool down enough, you're going to get rain instead. Yep. So there's a limit to the amount of moisture you can have in a given volume of air to produce precipitation. So the maximum heaviness of snow is always going to be less than the maximum heaviness of rain.
Jeff in Southminster says, hello Chucklebun, a question for the scientists. What causes the northern lights? Where do they come from? Etc. And why so many colours and seem to cover so many miles of the sky? Jeff in Southminster. Thank you for your challenge to Dr. Dave. Dave?
Okay. Northern lights, in fact they're both the northern lights and the southern lights, it's symmetrical. They're created when particles are thrown out from the sun, so you get sort of huge explosions in the sun, and they throw out charged particles. These are mostly either electrons or sort of charged hydrogen atoms, so protons. Charged particles are affected by magnetic fields, and they tend to follow the magnetic field lines. So if you imagine a bar magnet, if you've put it on a load of iron filings, you see the sort of lines which the iron filings produce follow the lines of magnetic field. So the Earth is a big bar magnet, and so these charged particles tend to try and follow these lines of magnetic field, and they all pile into the North and the South Pole. So you get a concentration of these charged particles from the Sun piling into the North Pole and the South Pole. Now, when these hit the atmosphere, they've got a huge amount of energy and they dump it into the gas in the atmosphere. And there's nitrogen and oxygen gas makes up most of the atmosphere and gives the atoms energy, and they release that energy in the form of light. Depending on how much energy they get can affect which colour they get, and depending on the energy of the particles coming in can depend which colour you get out and which gases will re-radiate the energy. So I think sometimes the colour you get depends on what kind of particles are coming in, because different particles have different energies and or the amount of energy they've got as to what colour of light you get from the gases. It's the light that's produced in a very similar way to the light in a neon tube, but sometimes if you give it more energy you can get a different colour out of the atmosphere.
They're really spectacular as well. I haven't seen them.
I've never seen them. I'd love to.
Yes, that's one of those things. Maybe a short holiday together then, Dave. Let's carry on with your questions here. Ken says, could you ask the Professor, is it possible to create lighting artificially? And if so, what sort... lightning. Beg your pardon, lightning. And if so, what sort of power could this generate?
You can certainly produce you can produce something analogous to lightning. You can produce various ways to produce a huge amount of charge
Frankenstein.
somewhere. Bit like Frankenstein, I guess. You can do it with Van de Graaff generators you might have seen at school. They're things with a little motor in the bottom and they've got a ball at the top.
Oh, yes.
And you touch them and your hair stands on end.
Right, yeah.
That sort of thing.
Yeah.
You basically, if they work because they've got a rubber belt, you put charge on at a fairly low voltage at the bottom, and then it kind of takes it all the way up to the top, and then it drops it off at the top. And that way you can sort of pool charge up to higher and higher voltages, and you can get up to a couple of million volts like that. Certainly one way of using very high voltages. You can do it with really, really powerful transformers, the sort of things which you plug into the wall to charge your mobile phone, which are converting mains electricity into sort of 5 volts, which your phone likes. You can run the other way. And I've got one at home which will produce 10,000 volts, and you can get others which will produce a couple of 100,000 volts. Those will produce pretty big sparks. They are used to test how well... There's a big one in Germany, I think, which is used to test how well cars and other things survive being hit by lightning. I think particularly the electricity grid, because it's quite important that will survive being hit by lightning, because it's an obvious place to get hit by lightning. But actual for uses, you're never going to generate more electricity than you put in. All of the means of generating very high voltages are really quite inefficient. You only get a few % of the energy you put in out as high voltage electricity. So apart from looking cool and testing things, and you can produce really, really beautiful patterns with them. Because if you strike a piece of plastic or a piece of paper with a lightning bolt, you get sort of a tree-like pattern out, which I think sometimes people sell as a rather beautiful effect. But other than that, it doesn't have a major use, I don't think.
Now, Dr. Dave, Tony says, Dr. Dave, just talking about the current going through wires to light up a bulb on a bigger scale, though, how do they get electric signals to go to America by cable?
I guess these days they don't do it very often. They've been sending signals to the States by using copper cables for a long time, ever since the middle of the 19th century. Basically, they have a very, very, very long cable. Originally, they did just have a simple, straight, long electric cable, and you connected it to a battery at one end, and at the other end you had a very, very sensitive detector and measured the very, very small changes in voltage. And from that you could send telegraph signals. Essentially, there was a very, very big resistance, but if you have a very, very small current, you don't know the big resistance doesn't produce a very large voltage drop, because you're not trying to push very much current through it, so you can cope with a very large resistance, and so it still worked. As time got on and they wanted to get more information down the cables, because putting a cable under the Atlantic is exceedingly expensive, they started off trying to send essentially radio signals down a cable across the Atlantic. The problem with those is they do die out as you go across. And so they had to put in amplifiers every few kilometres. So you'd send a signal in here, and then 20 kilometres down the line it would get amplified and then cleaned up and sent off again, another 20 kilometres amplified. And so and then you'd have just some power cables running along with your big cable to power them. And so that got a lot more information down. You could get maybe 1,000 telephone calls through a cable across the Atlantic, with a few coaxial cables with radio signals going down them. And then now they don't bother with copper cables to transfer information beyond from your phone to the exchange. These days they use fibre optic cables. So instead of sending electricity down the cables, what you're actually doing is sending pulses of light down a very, very thin piece of glass, which traps the light in it, and you can make it go around corners, which follows this tube of glass. And you flash the light on and off up to 10 billion, probably 40 billion times every second these days. And you can send signals, a huge amount of data down a very thin piece of glass.
Amazing, isn't it?
And then they need amplifiers regularly all the way under the Atlantic.
Let's carry on with an email this time from Nigel, who says, "Hi, Professor. I seem to remember reading that Tesla was fond of loading himself up with thousands of volts and also proposed a universally free source of electricity might be available. Was this just excessively expensive, ahead of its time, or just not viable after all?" Dave?
Nikolai Tesla was a very bright bloke. He invented the way, basically AC electricity. He didn't quite invent AC electricity, but invented the way we do it today, with the 3 phases. You get 3-phase electricity. So if you have a very large factory or building, you get electricity, AC electricity, so vibrating backwards and forwards, current going backwards and forwards, and you get 3 different phases where you vibrate backwards and forwards in slightly different times.
Yeah.
And Nikolai Tesla invented that, and he invented 3-phase motors, which are incredibly efficient and can get much smaller than normal motors. I don't think he made a lot of money out of the experience because someone managed to get the patents off him at the inappropriate time. I think Westinghouse. But yes, he also later in his life he developed a thing called the Tesla coil, which is basically a very high frequency, very high voltage transformer. You might have seen these on TV or something. You get sort of a mushroom-shaped thing with great big sparks coming out of it.
Oh, yeah.
They sometimes have a Teslathon in Cambridge where you can go and watch people making a horrible noise with lots of big Tesla coils at the Museum of Technology. I think it happens in October. It's quite an interesting experience. Although slightly scary in its way. And he would, if you've got a path for that electricity to go down, then you're quite safe. And so he would do sort of stage shows involving huge sparks and scare everybody and enjoy himself. And he did manage to blow up one of his machines, and I think he thought there was some way of getting energy out of these high frequency, high voltages. The general theory is that he managed to just do something which he wasn't expecting, and it was probably almost certainly obeying all the laws of physics as we understand them. It's just he didn't understand the machine he was building, and it managed to blow itself apart. There are still people who think that there's a way of generating free energy, but in general, if anything sounds too good to be true, it normally is.
They'd never let us believe that anyway, Dave. Who have we got here? Jim on Canvey Island has said, question, if you put boiling water into a glass tumbler, would it break? Something we're told never to do, Dave. Yes.
I think the answer is maybe, which is why you're told not to do it. The problem with glass, and the reason why it's not is used in all sorts of engineering situations, is it can be incredibly strong. It can actually be quite flexible. If you can actually stand on a sheet of window glass, and it will bend by sort of an inch or two in the middle, and it's a lot more flexible and a lot more elastic than you expect it to be. Most of the time.
Yes.
Unless there's a scratch in the wrong place and you happen to be trying to open up a crack, at which point it just breaks all at once and shatters. So glass is incredibly strong until it isn't, and it's very hard to know when that time is, when it isn't going to be very strong and it's going to break. The reason why you're told not to put hot water into a tumbler if you put very, very hot water into a glass and you heat up one side of it very quickly, as the glass heats up, it expands. So you end up with half of the tumbler the inside half of the tumbler being expanded, and the outside of it being stretched by the expansion on the inside. And if that stretch happens to open up a crack enough, you can then get a crack. Then that crack can expand and expand and expand until the whole lot goes crack. And you can it won't shatter. It probably won't shatter into lots of pieces, but you can end up cracking it all the way around, and you're ruining a perfectly good tumbler. So depending on the tumbler, it could be fine 99% of the time, except for that one time when it isn't and it cracks. If you've got a grotty tumbler with lots of scratches on it, or you just have to be unlucky, then it will crack. It could crack first time. Right. And things of glass, you never know.
You never know. All right, thanks for that, Dr. Dave. On the subject of electric, says Lizzie, we've had a lot of sparky stuff tonight. She says, is it possible for a horse to actually enjoy getting shocks off electric fencing? Even on the strongest, fastest setting, her horse still barges through it. From Lizzie.
I'm not sure I can really comment on the psychology of horses, but it's quite possible that the electric fencer isn't actually putting a very large current into the horse. If she's learnt how to push through an electric fence, which is not to touch it with your nose, because if you're a horse and you've got a nice wet nose, that produces a lovely conducting path of electricity to go through the nose into all the very sensitive nose, into sensitive bits of the face, and it's a thoroughly unpleasant experience for animals. But if instead the horse is pushing it with a load of dry fur, which is quite a good insulator, then and also will spread out the electric current over the whole of probably the front half of the horse, whole of her chest, then she's probably not getting a very bad electric shock. I know when I was a kid I worked out that if you touched an electric fence which you had in the garden with your finger, it hurt like hell. But if you grabbed hold of it with your whole arm, you just kind of jogged you a bit. But it didn't hurt too much. I'm
quite concerned about you, Dave. The picture of you having to be kept in as a small boy by an electric fence is quite scary. Go on.
To keep the rabbits out of the vegetable patch.
Oh, right, OK.
My dad used to be a farmer. These things happen.
Oh, fantastic, yeah.
Electric fences were the way you keep stock out of arable fields or arable patches. And the reason is that if you grab hold of your whole hand, the electric current is spread out over your whole of your hand, and so there's no place where it's really, really concentrated. So it'll make your arm jog, but it doesn't actually hurt too badly, especially if you've got a slightly weedy electric fence like we did. But if you touch it with the end of your finger, like you normally try and do, all of the electric current which is going into you is concentrated in one little place in the centre of your finger. And so that bit of your finger really, really hurts. And also your finger is particularly sensitive. So I reckon the horse has just worked out that if it barges it with its sort of chest and shouldery bit, which hasn't got too many nerve cells in there, it's not particularly sensitive, and it's covered in lovely, probably especially it's a particularly shaggy horse, lovely insulating fur, it probably doesn't really notice it.
All right, one here from Jeff, who says, how do speed cameras detect the speed of a vehicle? He has an idea it's something like a Doppler system, a frequency change or something like that, Dave.
Yes, most speed cameras do work on radar. Radar is a kind of a radio wave. They send the radio waves out. When they bounce off a car, they change their frequency, effectively their pitch ever so slightly. And so if you have a detector to pick up the radio waves coming back, and you can detect changes in the pitch, if there's a big enough change in the pitch, then it will know something's moving very quickly. It's a similar effect to although actually quite different effect because it's to do with radios rather than sound. So if you've ever driven past an ambulance going past, as it comes towards you, it's high pitched. As it goes away, it goes to a lower pitch. It's because as it's moving, the sound waves, as it moves towards you, the sound waves sort of, every time it makes a new sound wave, it's a bit closer and closer, so they're closer together, so they hit you quicker.
All right. And
as it goes away, each time it sends out a new wave, they're further apart, so it's further apart, so you get a lower frequency as they hit you. And so, they can use that. They can use the Doppler effect with radar. They can also... and then once they've worked out the car going quite fast, because it's quite hard to calibrate, it's quite a sophisticated piece of equipment, they tend to actually, for the court of law, they take two photographs. a known distance of time apart because it's very easy to make very accurate clocks. And then the reason why they've got the lines painted on the road is they take two photographs in quick succession, and they look at how far you've moved in between the two photographs. And if they know how far you've moved in a certain amount of time, they know how fast you're going. And that will stand up in a court of law. More recently, they've come up with laser speed cameras, definitely ones which policemen carry around, which essentially they have a thing called LiDAR, which sends out little pulses of laser light, and then they bounce back, and it measures the time it takes for the pulse to get out to the car and then bounces back again. And then if it measures how fast that time changes, that's measuring how fast the distance is changing. And so you can measure how fast something's moving.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.